In this video, we are going to study the extremely important concept of changing the basis of a matrix. Okay, this is different from changing the basis of a vector. So let me explain first what changing the basis of a matrix means. Let's say you have a transformation, a linear transformation, and let's say that this linear transformation is represented by a matrix M. So as you know, this linear transformation takes a vector input and it converts it into another vector, which is the output. Okay. Now, this vector input and this vector output, you usually write it as a column vector with the different components. But of course, those components depend on which basis you choose to represent these vectors, right? Which means that the matrix M that represents this transformation will also depend on what is the basis that you choose to represent the vector v and w. Okay? In other words, if your vectors are written using a different basis, let's call them v prime. So it represents the same vector but in a different basis, which means that the actual numbers inside the column will be different for v prime. So then you apply the same linear transformation and you will get the vector which is the same vector but written in a different basis, omega w prime. And this means that the matrix that represents this transformation will be different. It will be the matrix M prime, even though the transformation that it represents is the same. So let me clarify this with an example. Imagine we have a transformation which is projection into the x-axis. So this is our transformation. Okay? And this is how this linear transformation behaves. Any vector v, you apply the linear transformation a, and a of b is the projection of the vector into the x-axis. Okay? That's how it works. For example, if you want to consider the vector v equal to x hat plus y hat, which is this vector v, x hat plus y hat, then the projection of this vector v is the vector x hat. Okay? So that would be an example. So let's write it down. If we have the vector x hat plus y hat coming in, the vector coming out will be the vector x hat, the projection into the x-axis. Excellent. Now, let's write these vectors as column vectors in a certain basis. So for example, we could write this vector x hat plus y hat, we could write it as vector 1, 1 in the basis x hat, y hat, right? That's what we have been doing all of the time. And this means that this vector 1, 1 is going into this linear transformation and it's coming out of the projection as vector 1, 0 in the basis x hat, y hat. Okay? And using this basis, we know that the output vector is equal to a matrix multiplied by the input. So our output 1, 0 is equal to a matrix which represents the transformation multiplied by the input. And in this case, for this transformation, the matrix is 1, 0, 0, 0. This is the matrix M, which represents this transformation in this basis. Okay? So this is the matrix M. Okay? Because in general, if the input vector instead of being 1, 1 was x and y, the output vector would be x0, which corresponds to projection into the x-axis. But let's leave it as this concrete example. When the input is 1, 1, the output is 1, 0. Now, what if we write the vectors in a different basis? Okay? So why don't we use the basis b1, b2? Okay, and let's say that b1 is equal to the vector 1, 1, or let's write it, so b1 is equal to the vector x hat, y hat, x hat plus y hat, while b2 is equal to the vector x hat minus y hat. Okay, this is a valid basis. And therefore, now if we want to write the vector x hat plus y hat in this basis, the answer is that obviously this corresponds to the vector 1, 0 in this basis, right? Because it's equal to 1 times b1, which is x hat plus y hat, plus 0 times b2. So the answer is x hat plus y hat, which is the input vector that we are having, okay? So even though we are writing it differently, it still represents exactly the same vector v, x hat plus y hat, but it's written in this new basis. So now this vector is coming into our linear transformation, which is the projection into the x-axis. And we know that the output of this transformation must be necessarily equal to x hat, which we have here, right? Because remember, when the input is x hat plus y hat, the output has to be x hat. And we already knew this from seeing it here. So therefore, we need to write x hat in this basis, b1 and b2. So to write x hat in this new basis, the answer is that this is equal to 1/2, 1/2 in the basis b1 and b2. If you want to check that this is true, go ahead, but basically 1/2 b1 plus 1/2 b2 is equal to 1/2 x hat plus y hat plus 1/2 x hat minus y hat, and if you do this operation, this is simply equal to x hat. Okay, so indeed the vector output is 1/2, 1/2 in this new basis. Okay, but this means that now we have a problem, and the problem is that our matrix M will have to be a different matrix, right? Because we need this matrix to fulfill that the output vector 1/2, 1/2 is equal to this new matrix multiplied by the input vector 1, 0, where everything here is written in the basis b1, b2. So this new matrix that represents the linear transformation, we can call it M prime. Okay. Now remember, M prime represents a projection into the x-axis. Okay, it didn't change, so the transformation is the same. What changes is the representation that we are using for this transformation. Okay, so what is M prime in this new basis, b1 and b2? And that is the question I'm going to address now. So what are the 4 elements of this matrix such that the operations now work when we are working on the basis b1, b2? Okay, so this is how you can calculate M prime. First, you need to understand that v and v prime represent the same vector, like for example x hat plus y hat, but written in 2 different bases. So maybe v represents this vector 1, 1, while v prime represents vector 1, 0 in the basis b1, b2. So they are the same vector, but they are written in different bases. And the same with w. Okay, and therefore we know that we can use a change of basis matrix to write b and v prime, to write the relation between v and v prime, right? So if you recall from the previous video, we know that v is equal to a times v prime and that w is equal to a times w prime, where a is the change of basis matrix. So let me write it down. Okay, and so that is what we know. What is our aim? So our aim is that we know that W is the output when the input is V and the matrix is M. So W is equal to M times V. But at the same time, we know that W prime is the output when the input is V prime and the matrix is M prime. So W prime is equal to M prime times V prime. Okay, so we know that those 2 things must be true. So combining this with this, we can find an expression for M prime. So this is how we do it. Our starting point is that W equal M times V. That's our starting point. Now we substitute the fact that V is equal to A times V prime and W is equal to A times W prime. So we substitute that, and what we get is that A times W prime is equal to M times A times V prime. Now we multiply on the left by the inverse of A. So we do A to the minus 1 multiplying on the left, on both sides, on the left and the right hand side of this equation. So we get that inverse of A times W prime is equal to inverse of A times M times A times V prime. And now we realize that the inverse of A times A is the identity matrix, which is like not doing anything, so we can remove them. So we see that W prime is equal to this product of three matrices multiplied by V prime, which is exactly what we wanted to obtain matrix M prime. So matrix M prime must therefore be equal to the inverse of the change of basis matrix times the original matrix in the original basis times the change of basis matrix. Okay, and this is the recipe to calculate the matrix in a different basis, or to change the basis of a matrix. Okay, now this was very involved, but I think that the logic it makes perfect complete sense, right? But a common mistake is if the vectors V prime, so if the vector V is equal to the change of basis matrix times vector V prime, it's very easy to think that given a matrix M, to change the basis you just have to multiply by A, and that is wrong. Okay, that is wrong. That is ignoring the fact that you are changing both the input and the output of the matrix. So let's remove this, which is wrong. This is the equation for the change of basis. Now, apart from this logical derivation that I wrote on the left, I can do it more intuitively in a different way. So let me write the final form of the equation. So W prime is equal to the inverse of A times M times A times V prime. Okay, but now we can group things. So V prime is the input vector in the new basis. That's clear. But when we multiply this vector times A, we see that this group here, this parenthesis here, is A times V prime, which is equal to V. So this is the input vector in the old basis, right? So we have changed from a new strange basis to our old maybe x hat y hat basis, yeah, by multiplying times A. Now this input vector in the old basis, which will be in this example 1 1, now we can multiply it times our matrix M, which is known, to get the output vector in the old basis. Therefore M multiplied by this input vector in the old basis, this is equal to the output vector in the old basis. So this parenthesis here, all of this, would simply be equal to this. And now as a final, So now as a final step, we need to write it in the new basis. So what we can do is we can multiply this by A to the minus 1 in order to write it in the new basis. So this block here will be the output vector in the new basis. Okay, so you can see that the logic, it makes perfect sense. In fact, I like to draw a diagram where I write, in the first row I write the old basis, and I write the input on the left and the output on the right. So this is our matrix M in the old basis, okay? But now in the second row, I write the new basis. So this new basis, we have the input vectors and the output vectors, and we want to find this M prime, which relates vectors in this new basis. But fortunately, we know about the change of basis matrix. So we know about the change of basis matrix A. And this change of basis matrix A, it gets vectors in the new basis and transforms them to vectors in the old basis. So this matrix A does this. And it does it both in the input and in the output. And then the inverse direction is the inverse of A. This would be the inverse of A. So with this diagram, you can see that you have the old basis on the top and the new basis on the bottom, and they are related by the change of basis matrix and by its inverse, depending on which direction you are going. While M is applying the linear transformation. That's why you have the input on the left and the output on the right. So now, M prime, you can either go directly like this, or you can say, okay, I first do A, then I do M, and then I do A to the minus 1. So you first do A, then you do M, and then you do A to the minus 1. And I'm writing it from right to left because that's the order in which matrices are written when you apply consecutive transformations. Yeah. So first you do A, you move here, then you do M because you do this, and then you do A to the minus 1 because you do this. And this is equal to M prime. So once again, the same equation is proven. Okay, so I showed you several different ways to arrive at the same result. That to change the basis of a matrix, you need to use the inverse and the change of basis matrix on both sides. Okay? Good. I hope that was clear. See you in the next video.